Welcome to Virtual Humans, Lecture 11.1, Human Behavior Capture. In this lecture, we will see how to capture humans in static scenes. We will see how to capture dynamic human-object interactions. And finally, we will see also a method to capture humans in large spaces, like buildings, including several rooms and so on. So basically, like in terms of modeling the human behavior, analogously to modeling the human appearance, we have like two intertwined problems. One is we have to be able to capture people. This means like reconstruct their 3D motion in conjunction with the 3D scene when they are performing actions. So by this, I mean like we should be able to, for example, capture an interaction like this one, like this person capturing, grabbing a book and then moving to another place. And the difficulty here lies in being able to record the human motion in conjunction with the 3D scene. And we will see some techniques to do this. Now, capturing itself is really challenging because now you have like occlusions of the object and the human. You have to, for example, localize where the human is in the scene. So this is challenging in itself. And generating human motion that is coherent with the scene is also very challenging, and it's a topic that is becoming more and more important. It has many applications, as we will see. So here we mean like we should be able to design like an algorithm on an AI system that is capable of performing human motion coherent with the scene. So for example, this is an animation that is aware of the 3D environment, and so the simple model moves according to this environment. All right, so in this lecture, we will focus more on the capture part, and the synthesis part we will cover in the next lecture, which is lecture 12, Human Motion Synthesis. So why are we interested in human-object interactions? Well, most of the interesting human activities involve interaction with other people or with the world. We interact to change the environment in order to achieve a particular goal. For example, like we want to carry a box from one point to another, or we want to sit on the environment like a table or a chair, or want to hammer a nail, or want to open a box. Of course, like a very important type of interaction is like interaction with other humans. Unfortunately, due to lack of time, we will not cover these human-human interactions in this lecture. In terms of applications, of course, one obvious application is that robots could learn from human motion. They could learn from human demonstrations. And first of all, we need to be able to digitize these human actions with environment. Then, of course, like humans too can learn useful skills using virtual environments. For example, train people how to operate tools and machines in a virtual environment without the danger of actually performing the action for the first time. For example, like if the machinery could potentially be dangerous. And another cool application would be to have a virtual assistant which can help you navigate the world a little bit better. Imagine like joining and going to a new building, and you have to meet a particular person, and the virtual assistant would attend you at the entrance of the building and would show you the way through the building. So these are all like potential applications. Another application might be like for virtual teaching. For example, like you could have like, a famous character like Albert Einstein teach you a class on relativity and so on. So you could basically have these shared spaces, and basically the recent pandemic has raised like basically even more interest in these virtual spaces to communicate with other humans. So when we communicate through Zoom, the obvious thing that is missing is this this sensation of shared space. So these are all like potential applications which require being able to capture humans and objects. So how do we capture this human-object interaction in the real world? So, well, first we need to capture the 3D scenes, and here the computer vision technology has advanced significantly in terms of sensors and also in terms of algorithms. So we have lots and lots of, or not lots, but basically much more 3D data than we used to have, let's say 7 to 10 years ago. So one way is to, like, for example, like use Kinects. You can go across a room and then fuse all the depth frames into a single coherent 3D scene. You could use like different kinds of laser scanners. You could use scanners based on stereo or on LiDAR, and with this you can reconstruct the scenes that you see here. And then, like for example, like some works came about when these 3D scenes were available. Like, for example, this is the work of ICCP-19 Prox, which basically like argues for incorporating the 3D scene to estimate the 3D human pose and shape from images. And the argument is that if we know the 3D scene beneath, like we can estimate the human pose better because we know the humans do not intersect with the scene. We know that humans perform certain types of actions with particular objects and so on. So in the simplest form, we can enforce these physical constraints, and this is basically what Prox is about. The idea is to estimate the simple model using similar techniques to simplify, which we saw a couple of lectures ago, but at the same time, we incorporate constraints such that the simple model should not penetrate the 3D scene, and for example, like certain parts of the simple model should be in contact with the scene. So this improves the results because, for example, like if you don't take into account the scene, you have like penetrations like this, so the person is sinking into the sofa, which is clearly not correct. So basically, we want to penalize intersections, and we want to use contact. In this case, in Prox, like those contacts are manually annotated. So the vertices in the simple model are manually annotated to, so they define which regions will be most likely in contact with the 3D scene, and then basically they encourage proximity if contact vertices, this blue vertices are close to the scene. How you do this? I mean, this is ways like you could just have a constraint that says like these vertices should have a distance close to 0 to the scene, and to enforce penetration, you typically would minimize like the distance from the simple vertices, like the sign. You would basically make the sign distance be 0. So you would detect which vertices of the simple model have penetrated and then push them out by minimizing this distance. And so basically this is essentially based on optimization, and here the 3D scene is not estimated, is assumed to be known. And basically like they prove their hypothesis that basically empirically they show that the results can improve if you know the 3D scene in advance, which makes a lot of sense. So basically Prox captures a static scene, but the question is, of course, how do we capture dynamic scene interactions? How do we capture a human moving the objects in the scene or moving like a particular object? So how do we capture this kind of data? Using a single image, it will be very difficult because we have lots of ambiguities, and tracking the human and the object is really challenging. There are methods, and we will see them, but it's really challenging. So one option is to use marker-based capture methods, which are high quality, but they are also expensive, and they are limited in the recording volume, and they are not easy to scale to large spaces. And also markers from an optical marker system, those markers that you place in the body, like they can be also occluded, especially during complex interactions. Well, another way is to put IMU sensors on the body and then basically use this camera-free system in order to track the person. And we will see a little bit of this technique later, which are IMUs are good because they are easy to scale and there's no restriction in the recording volume. You can record in large spaces, but they are prone to sensor drift, and the quality of the data is I would not say poor, maybe that's a bit exaggerated, but it's not as good as an optical marker system. And especially if you just do not incorporate any visual information like this, your data will basically drift away over time. So in this work, which is called Behave, we basically have like something in between. So we wanted to capture system that is portable, but it has also good localization and it does not drift over time. So for this, we used like a setup which includes 4 calibrated Kinects, and basically 8 subjects were recorded, 5 males and 3 females in 5 different locations. And we captured a variety of daily use objects and interactions. For example, boxes, chairs, tables, backpacks, and so on. So the data looks like this. You have an RGB sequence, and essentially Behave is an algorithm and a data set as well to capture like the human object interaction, and in particular the human motion represented as the simple model, as well as the 3D mesh of the object. So this is the Behave data set, which includes a wide variety of these complex interactions, which are dynamic because like the human is moving the object. Now, how is this done? This is far from trivial. This is a very complex problem. And how did we start? Well, we started by being humble and acknowledging that this is a hard problem. We wanted to collect good data. So essentially, like we designed a rather sophisticated pipeline, including a little bit of manual annotation in order to track the human object pose. So the annotation involves clicking points in an image that, so basically you have to identify key points of the objects such that then we can use these key points to reconstruct the object pose more accurately. Then using the Kinect data, like one can fit the simple model to the point clouds. We're using techniques that we've seen in the class, like for example, like registration. And then like basically you jointly estimate the human object pose and the human model. So to estimate the human model, we also use 2D key points coming from 2D detector, which is called Open Pose, and basically using the object fix and segmentation and the key point annotations from Amazon Mechanical Turk. Basically, you optimize the model such that the projections of the 3D joints of simple and the open pose detections match, and the 3D object points match with the 2D key point annotated in the image. Now, of course, this is a tedious procedure, which we needed to do to get things started. And then after this, we trained a model to automatize all this process and be able to automatically from 4 depth views of the human and the object to automatically recover the simple model and the object. So how do we do this? Well, typically, to feed a model to data, the classical way, you would basically minimize, as we've seen several times in the class, like the model parameters x, to minimize the distance between features extracted from the image, or in this case, the depth images, and the model. And if these features are the classical features that we all know, like edges, key points, and silhouettes, it's very likely that this will get stuck into local minima, especially for complex human-object interactions, because you have occlusions, you have matching ambiguities, and you have missing data. So these are some examples of the challenges. Sometimes the object is not fully visible, it's only partially observable, the Kinect data is noisy and incomplete, and you have all these problems. Sometimes, like, of course, contacts occupy only a very little portion of the pixels in an image, and contacts, however, are very important to the perception of like a good human-object interaction, but they are difficult to detect in the images. Of course, like the object can occlude the full body and making the task very challenging. And like you have for example, the right arm of the person is not even visible in the second image, making its tracking extremely hard. And it's a common scenario when dealing with these human-object interactions. All right, so what can we do here? Well, the key idea is to find features, F, right, that we can extract directly from the input point cloud, which make the optimization better behaved. So what do we do? Basically, we can predict at a high level. We can predict for every point in the 3D scene, like a correspondence to the simple model, such that we can then feed the simple model in an easier manner. This is an idea that is similar to some ideas we've seen before, like loop-rec, for example. And finally, we can basically fit the simple mesh. Sorry, this is playing automatically, and I want to stop it. Second. And then we can fit the simple mesh and the object to this, to this neural network predictions, which predict the correspondence field and a distance field. So let's look a little bit more in detail how this correspondence field and this distance field look. And again, these ideas are similar to this work that we saw in one of the lectures, which was called the loop-rec. So you might want to refresh your memory and check that again. Check that video if you're you don't remember that. So as for distance for the human, you can predict, like, given the point cloud, you can predict like a distance field of the human. So basically this sort of trains the network to ignore the object and to predict for every point in space what is the distance to the human model, right? So this is defined with this UI of h indicating human, and maps every point in space to the distance from P. This is the distance from P to the mesh of the model. Then you have like the distance field of the object, which basically is trained, the network is trained to ignore the human in this case. And then finally you have like this correspondence field. So for every point in space, now we predict the closest surface point CI. That's why you have this coloring here, so which are indicating that, for example, here, the closest point would be this right arm of the simple model. And so this is dividing the full 3D space into this body parts in a continuous manner. And then using these fields, you can optimize the simple vertices in order to be coherent with the human distance field, the object vertices to be coherent with the object distance field, and also leverage this correspondence field in order to make the meshes coherent with those neural predictions. So let's look at this in a little bit more detail. So basically, we know that the simple model should fit the input human point cloud, and for this you can make the your mesh match this distance field of predicted by the neural network. So what do we want? We want that the distance from every point in space Pi to the closest point in the simple model M of Ci, where Ci is also predicted by a neural network. We want that this distance for every point in space Pi, right, matches the neural network prediction of the distance, which is UIH. So this is what we want to minimize, right? This difference, this discrepancy with respect to the model parameters that parameterize M. And we also need some regularization term. And then we have the object term. We want that the object mesh lies within the zero level set of the neural distance field. This means that for all objects, for all vertices in the object, we want that this UJO basically is as close to zero as possible. That's why we have to minimize the absolute value of this. And to regularize things, like you can also minimize the distance in the chamfer distance from the object point cloud. Sorry, this is an automatic, sorry. So we want to minimize the distance from the object mesh to the surface which is with S, which is the point cloud captured by the Kinect data. And then we want to satisfy contacts. What is a contact? Well, contact is defined in Behave as any point which is close to the object and to the human. Close by some threshold, less than 2 centimeters in this case. So basically, you can know that it's a contact when uj of O and uh of j, or uj of h, is when both of these distance fields, are less than 2 centimeters. And again, like here, this for these contact points, we want that the vertex, right, of the object matches the point in the simple model, which is M of Cj. So these are the 3 constraints. And the good thing is that then you can obtain results that look like this, which look pretty much similar to sorry about that. Trying to pause the recording. All right, yeah, sorry for the interruption. So basically, like I was saying that after having trained the Behave method, you can get results that are almost on par with this semi-ground truth results we obtained with this semi-automatic method that included having to annotate the key points of the objects. So the Behave dataset is a dataset that is publicly available for research purposes. And yeah, I mean, so basically the community is picking up on this because there's a growing interest in modeling human-object interactions. Even with Behave, like we cannot capture every possible interaction with environment, particular interactions that involve large scenes. Because like capturing with external cameras imposes restrictions in the size of the recording volume, and also due to memory requirements, also on the time, like how long the sequences can be. So for these, like these IMUs that I was mentioning before are ideally suited. And for these, like there's work that is called Human Positioning System, or HPS, standing for 3D Human Pose Estimation and Self-Localization in Large Scenes from Body-Mounted Sensors. So what is the idea here? So the goal is that given a human that is moving in the 3D scene, like the method recovers like the human motion and can track the human motion within the 3D scene. So basically it does 2 jobs. One is estimating the 3D human pose, and second, it localizes the person within the 3D scene. So the goal is to capture a large, like interactions in large scenes and long recordings, meaning like recordings that could take up to an hour or even more. And for this, like this method uses wearable sensors, which require no external cameras. So the sensors that will be used are these IMUs and a head-mounted camera. So a camera that will be looking outside, mimicking or emulating the field of view of a real human. So these are the sensors that will be used, and basically we want to register the digital human within the 3D environment. And for this, this work pre-scans a large 3D environment and then localizes the human within this 3D environment. So in this case, this is an example of the environments considered in this work. This actually is a rendering of the 3D reconstruction of the Max Planck for Informatics in Saarbrücken. And as you can see, this is a building that includes different rooms. This is the library. So And then, like, you know, real humans will perform motion here. And the task is to estimate their 3D pose and also localize where they are in the scene. Well, the question is, how can we capture human motion and register it with a 3D scene? If we capture motion with IMUs, like, the problem is the following, like, the IMUs drift over time, and what happens after a while is that the human is not aware, or the reconstruction is not aware of the 3D environment. It ends up like flying in the air. So the key idea here is to combine IMU-based pose estimation with camera localization. So what I'm showing you here on the left, if you've never seen this, this requires explanation. So on the left, you see the picture of a real image. On the right, you see the picture of a synthetic image. So essentially, we have a 3D environment, and the synthetic image is the rendering of this 3D environment as seen from our estimated camera pose, the camera pose of the head of the person. If the real and the synthetic match, as is the case here, it means that we have estimated the camera well. This is solved using visual localization or self-localization. So this is one of these classical computer vision problems, which has many applications, as you can imagine, to localize, for example, like where a picture was taken. So the goal is, like, given this 3D scene and a single test image captured with a camera, in this case would be the camera placed on the head of the person, you have to figure out where in this 3D scene this picture was taken. That's the challenge. So how do we solve this problem? So in computer vision, like, this is typically addressed using 3 steps. So one is you have to extract features, distinctive features, which are based on deep learning. This might be key points, edges, and so on of the test image, right? Typically, key points are most of the times used. And then, like, basically you have to consider your 3D scene, which itself was, for example, like reconstructed using a scanner that uses multiple views of the scene. And so what you need to do is to extract features from these views that were used to reconstruct the 3D scene. And then basically, like, do feature matching to find which camera viewpoints in the 3D scan have the most similar features to the ones in the query image. So you have to retrieve similarly looking parts of the 3D scene using the features. And now, once you've extracted these viewpoints, you need to basically optimize the camera until the features extracted, like the features from the retrieved camera, from the retrieved 3D scene, match with the features of the test camera. So these are roughly the 3 steps that are necessary for visual localization. And so if you do this, results improve, like the person is not completely flying on the air, but you see that sometimes it intersects the floor, and sometimes it's not really matching with the scene, or it's flying a little bit above. So what is missing here is similar to Prox, a little bit of reasoning about the physical constraints of the scene. So we know that humans cannot fly on the air. We know that humans cannot penetrate the floor. And this is what is integrated in this joint optimization. So the optimization will optimize the simple parameters to match the visual localization head camera pose, to match the IMU measurements, and to match the constraints of the 3D scene. And basically using these 3 constraints, like, one can obtain like an estimate that is both coherent and it satisfies the physical constraints. So the objective function would look something like this, and this is optimization over a batch of frames, similar to this SIP work that we saw before. Basically, you have a self-localization term, match the 3D scene against the images of the head-mounted camera, a scene contact term that basically when IMUs detect a contact with the foot and the scene, so IMUs can detect these contacts with accelerometers. When you hit the ground, the acceleration will be very high, because, like, you will go from high velocity to 0 very quickly. So you can enforce that those vertices match the scene when the IMU tells us there was a contact. Then we want also smoothness so that the motion is not jittery, and we have like the pose term that makes the simple pose match the IMU pose. And the result is like a method that can track humans in the large scene. Basically, which was the first time this paper was selected as best paper finalist for was selected as a candidate for best paper award at CVPR 21, because most likely because these are results that people had not seen before. It's a new problem, and basically it shows what is possible. And like, you know, now with all this interest in the metaverse, one could very well imagine that this become more and more important, this being able to record human motion within the 3D environment and know where you are in the scene. So you could imagine that the 3D world is uploaded into the cloud, and then we navigate the world, and then at all times there's an algorithm that tells us where we are in the world, and maybe we can augment this world, visualized with some goggles or some VR glasses. Right, it can augment and then place virtual objects in the world, and so on. All right, so I mean, these are some of the results. Like you have different types of interactions, like interacting with a computer. And notice that here we're not using any external cameras. And so this is what makes it quite challenging, because we're only using the head-mounted camera and the IMU poses. So notice the thing that is missing here is actually the interaction with dynamic objects, and this is some subject of current investigations. And you can imagine that if you do not have access to external cameras, this is quite challenging. But there's some things that you could do. You could reason about the object motion based on the human, for example, and this is something that we are currently investigating. All right, good. So to conclude, basically capturing human-object interaction is important and challenging, and is a very hot topic right now. And Behave proposes a simple capture solution based on depth cameras. We've seen like that this combination of neural fields and classical optimization is a promising approach. And we've seen that external cameras are not suitable for long range or long time recordings. And for this, you can use IMUs and maybe combine them with self-localization. And we've seen this method based on joint IMU-based optimization, and self-localization can track a person using just body-mounted sensors. Thank you. And now we will move to human-object interaction capture from single images in the next sub-lecture. Thank you very much.